to update the seismic hazard assessment that we have for the facility. So this plot that you see on the wall right now is what we call a tornado diagram, and what we're looking at is the range of what we call sensitivity hazard, where it's basically a ratio of the hazard as given in the 2011 report as our base case, or 1, with the range of values that are also reported in that report. So for instance, for the Hosgri slip rate, which is the top of the tornado diagram, and the way this is ordered or ranked is the parameters have the highest uncertainty or at the top of the tornado, and then go down to the ones with the least at the bottom. So the Hosgri fault, walking into this work, had a slip rate anywhere between 1/2 to 6 millimeters a year. And that contributes to this wide range in values, where values greater than 1 basically indicate a higher hazard than what we had indicated in the 2011 report. Values less than 1 are a lower hazard. We identified 10 specific elements to investigate as part of the CCC SIP, or for shortened version, the AB 1632 project. And these were vetted with members of the IPRP during the early meetings of the panel. So the parameters that we're going to be talking about today, and the parameters that we measured as part of our marine program, are looking at the slip rate of the Hosgri fault, the slip rate of the shoreline fault. Both of these two fault systems are underwater and hence not accessible to conventional land-based paleoseismology techniques. We're going to talk about the step over between the Hosgri and San Simeon faults and the Hosgri and shoreline faults as part of their possible linkage, as well as look at the issue of the shoreline southern end. How long is the shoreline fault from its northern extension to its southern extension? So these are the primary topics of discussion for today. Other topics on this list will be presented in upcoming IPRP meetings during the months of November and December. And this is just for basically a reminder that we did discuss and vet these parameters with the group. This is a poster that the IPRP issued in, I think it was the fall of 2012. As part of the process, and here again, the Hosgri slip rate is sort of the #1 priority for evaluation as part of the project. Looking at senses of slip on the shoreline fault, intersections of different fault systems, and then what the total length of the shoreline fault is, was discussed and vetted.
That was a poster presented at an NRC outreach event in San Luis Obispo, which summarizes in fairly few words what was said in IPRP reports 2 and 3. Clarify what that is.
All right, good. Now I was just using this to establish a consensus among the group.
IPRP report. The IPRP has gone through these items on the tornado diagram and given recommendations. Okay. And discussed these.
Now, in September of this year, PG&E issued the Central Coast of California Seismic Imaging Report. I think all the members here of the panel received both hard copies, weighing in about 32 pounds, as well as electronic copies of the report. And to facilitate our wish to be transparent and have this information available to the public, it's also posted on the PG&E website, the URL to which is down here at the bottom of the page. Based on feedback that we've gotten from some of our users, we have supplemented this website now with additional instruction on how you can get the seismic data for evaluation should one choose. So these are the uninterpreted SEGWI files for the marine seismic and land seismic data. And all this is now on our updated website. This is a screenshot from the USGS web page, the National Archive of Marine Seismic Data. And what we show here is the screen where you can access the seismic data for the Estero Bay, Point Sal, and San Luis Obispo Bay studies That were the 3D studies that we did in 2011 and 2012. So this is a map of study areas, a listing of those particular studies. You'll see we have the Point Bouchon 2D and 3D listed there as well, and with instructions on how to access this data. A lot of these data sets are very large, so it's not easily downloadable, and in this case, for instance, it asks that you contact the site administrator to get a copy of the data. Similar thing with IRIS, which is the next slide. So this is the home for the land seismic data. This is, again, a third-party academic site run by the Incorporated Research Institutions for Seismology, and we put all land seg-wide data on the site. The waveform data is listed down here, and again, there are instructions in the PG&E webpage on how you can access that. So we've, again, in our interest to try to be transparent and make this information available to all who may have an interest. So get on to the marine side of the work that we've done. This is a schematic diagram of just how marine seismic process operates. And the top picture shows two types of data that we've collected and used as part of our project. One is called multi-beam echo sounding, which is basically high-frequency waves are used to map the surface of the seafloor. Not very much penetration beneath the surface, but provides us with very high-resolution imaging of the surface of the seafloor to construct improved bathymetry maps. To get beneath the surface of the seafloor, what we've done is use a process called low-energy seismic surveys, or LESS, where you have a sound source which generates sound that then reflects and reverberates off of buried layers beneath the surface of the sea, and then those reflections are recorded by a series of hydrophone streamers that trail behind the vessel. So the picture at the bottom is a shot of this survey in San Luis Obispo Bay in 2012, and you can see behind the vessel a series of 12 streamers that are about 50 meters long that are recording sound produced by the triple plate boomer, which is located just about here with respect to the streamers. So this is work that we did in conjunction with Fugro. It is a license. Yeah, it's licensed under the State Lands Commission, has a power source which is less than 2 kilojoules in energy and size, and this has been very instrumental and very valuable in helping us map the shallow portions of the seafloor, looking at recent geologic features, which at the end of the day turn out to be critical towards understanding the seismic hazard. Looking at recent geologic offsets, recent geologic features, you can not only get a sense of where the active faulting is occurring, but also allows us to get a sense of how fast these faults are moving in recent time, within tens to hundreds of thousands of years. So this is one of the key pieces of information that we need to do. Seismic hazard assessment, as you saw from the tornado diagram, some of the key uncertainties related to these faults. So this was a very successful part of our 3D adventure. This is a comparison of where we were and where we are today. So the panel on the right is a bathymetric map that came from the original LTSP report, and it really captures the state of the art in the late 1980s, producing contour maps based on soundings, and then using that as an interpretive tool for offshore hazards. The panel on the right is the multi-beam echo sounding mapping that we've done as part of the LTSP, but we've used this information now as part of our AB 1632 studies, and you can see just the difference in resolution is astounding. The feature between the two red arrows here on the right-hand panel is one segment or expression of the shoreline fault zone right offshore Diablo Canyon. So the distance between here and here is on the order of about 600 meters. Probably one of the other frontiers, if you will, for bathymetric mapping is what we call the white zone, the area between the shoreline and where you could safely operate a marine vessel without having to worry about hitting shallow rocks or getting props snagged with kelp and other debris. We've worked with the Seafloor Mapping Lab at CSU Monterey Bay to fill in a lot of this area over the intervening years. And again, showing how we have tried to access, take advantage of the latest technology to use the best information that we could to address the problems before us. So what I'd like to do now is, in the next two slides, is just review the project areas that we did work in as part of this, and just the areas, the topics in white are the ones that we're going to be discussing today. The topic areas that are grayed out are the topics for further discussion in either November or December. So in 2009 and 11, right after the announcement of the recognition of the shoreline fault, we started doing low energy seismic survey work to better define the northern end of the shoreline fault, which is located right here, parallel to the coastline, where it's the nature of its intersection with the Hosgri fault, which is located here. And the Hosgri is regarded as the controlling or principal seismic source offshore Diablo Canyon. And Diablo Canyon is located right about there. So work to the north to define the nature of that intersection with the Hosgri, and then starting to do work in San Luis Obispo Bay to the south to define what the southern extent of that fault zone was in the bay. In 2012, we continued doing this work based on results that we got from the 2010 and 11 field season. We discovered that, in fact, there were paleo channels that came across the continental shelf that gave us an indication we may be able to have piercing points, basically geomorphic features that are cut by active faulting, and looking at the offset of those features can give you an idea about what the slip rate was. Gary Green will talk about that a little bit later. So based on these initial results we got in 10 and 11, we decided that it was a good use of resources to go and see if we could develop more information to better determine the slip rate here for the Hosgri fault off of Point Sal, the Hosgri fault further north off of Point Bashan, as well as the shoreline fault here in San Luis Obispo Bay. And remember, all these are underwater. So the only point that we had heretofore was up here in San Simeon, with which to get a fault slip rate. The rest of this fault is basically inaccessible until we started doing this work. And again, areas in gray, the onshore seismic work will be discussed in November. So this is just a simple schematic diagram of what you can do with 3D data, what you can do with digital data. And this is from a block that was acquired in San Luis Obispo Bay. And just very quickly, you have this 3D volume or cube that you assemble. You can strip off the water layer to look at the seafloor itself. You can identify a particular horizon at depth, and then strip off the overlying sediments to interrogate the horizon in more detail. In this example, what we're looking at here is the actual bedrock surface. In this case, the pre-Holocene, the pre-Quaternary bedrock surface in the middle of San Luis Bay. And what this shows is the trace of the ancestral San Luis Obispo Creek as it cut across the continental shelf during the last low sea level stand. So it's this kind of data that we can use and interrogate to address the questions that we've identified in the tornado diagram. And with that, I'd like to hand this over to Dr. Green, and we can talk about some of the results in the marine seismic work.
Wow, 94.4, I'll be precise.
We don't want to put you to sleep.
I don't think my laptop would even load that.
It's consistent with the 32 pounds. Data rich.
Probably talking.
Thanks, Stu.
I'm Jerry Green, and actually, I don't know if I should be saying that here or not, but I've had a lot of fun working with this data. This data has been fantastic data that I think every scientist should get copies of to work with, because it's been a real pleasure to work with that. And basically, the objectives of my reporting here is to report upon two studies primarily: the Point Vachon study and the LES that was undertaken in regard to AB 1632. The Point Vachon report has been reported to you before, so I'm not going to spend a great deal of time on that. I'm just going to review that to bring you up to speed to show you how we're dealing comprehensively with the shoreline fault. And then also to present results of mapping the extension of the shoreline fault zone and estimating the slip rates on the Hosgri and the shoreline fault zones as well. Now this is, even though I've had a great deal of time, fun doing this, this has really been a team approach. And we've had several different teams involved in this. For the Point Vachon team, Fugro, LCI and Mossman Marine Laboratories were the primary investigators, and Michael Angel, Justin Pierce, Hans Abrahams Ward, and myself worked on the interpretation of that data for the Point Vachon report. And the last data, again, it was Fugro, LCI, and MLML, with Phil Hogan, Hans, again, and myself working on the interpretations of that data. Stu was the technical coordinator of this, and as you heard, I sort of led the teams. I want to point out that the team members are here. Hans is right here on my right, and Phil further on down. And although I'm the spokesman, I would like to ask them to keep me in line. If I go off on a tangent or something like that, they might jump on me and say, no, this is not how it is. And so I invite them to do that. And as we get into the details, hopefully I'll be able to go through these slides relatively fast, and then we can dive into the details of this thing, at which time I certainly would ask Hans and Phil to participate. And you can address questions to them just as well as to me as well, if that's all right with you guys. Okay, that's fine. Okay. So let's talk about the surveys here. Sue actually introduced them to you. The first survey I'm going to talk about is the Point Vachon survey, which is shown here in purple. And then the Estero Bay, Point Sal, and San Luis Obispo Bay. Now the different colors here means that the Point Vachon is a 2D, 3D survey that was undertaken. These are all 3D efforts. The red areas are areas that were undertaken using the P cable for 3D, and the blue area is where 4-channel 3D data was collected. And I'll talk a little bit about the configuration of the receiving and sources for that, those surveys. This is basically, these areas were laid out based on several different things. Where the fault lies, obviously, as was mapped prior to our work, and in areas where other data, such as the USGS data, showed that there were buried channels. So we selectively picked areas that had channels. We knew channels were there, and we thought channels would be a good piercing point to look at to try to get offsets. In addition, we collected 3D data here in the blue box and discovered that there was a series of channels in here that we wanted to go look at. And so we added this red box to look at that, as well as to look at where was the southern terminus, if you like, of the shoreline fault zone. So that was the objective of how we laid out these surveys and undertook the work.
Before you move on, Gary,
yes.
A couple comments. There's channels and there's channels, and we've talked a number of times about analyzing the channels. You've shown the example of the channels that are from the low sea level stands that were carved by creeks, by subaerial erosion that we're all used to. But then in deeper water, these are submarine channels that were formed by different processes and farther offshore. So you don't necessarily expect them to look exactly the same in your surveys as you do the subaerial channels. So that's one thing that I think we need to be aware of, that when we're looking at the channels on the shelf in the San Luis Obispo Bay as a different kind of beast as the other two surveys.
Absolutely, yes.
The other comment is this, if you want to, can you switch back to that last picture? Because you're
I'm not a PC guy.
You're intentionally showing a map of the faults as you thought they were before these surveys. And
Sorry.
It's useful to show that map, but then way on towards the end of your presentation, you have a comparison map where you've extended the shoreline fault to the southeast. And so it just to kind of let people know that this fault map is the pre-investigation fault map.
Correct.
Changed towards the end.
Correct.
That's one of our recommendations early on was to investigate the southeast end of the shoreline fault. And that change, which you'll show later, right, is not here on this map.
Right. Yeah. I do have examples.
Yeah, I was paging through your
Skipping ahead, Chris.
I wanted to make sure that that's mentioned, that this fault map is not the final fault.
Right. Right. Yeah. Thank you for that. Okay, so I'm just going to briefly go over the configuration for collecting the data. In the initial work, the work that we did in Point Luchon area, and some of the work we did to the south was the data were collected using 4 streamers and a 3-plate boomer. We actually operated that boomer at about 1.5 kilojoules, so we were below the 2 kilojoules. Thus, the qualification of low energy seismic survey that Stu mentioned. And then for the other work that we did, the true less work, if you want to call it that, is that we used the P cable. The P cable we evolved at the time we were doing the previous work, and so to take advantage of the state-of-the-art type of technology that was available, then we shifted over to the P cable, and we used up to 14 channels. In this case, again using the same source, which is the low energy triple plate boomer source.
Harry, that's 14 streamers.
14 streamers.
Each streamer had 8 channels.
Right. Okay. 4 streamers. Yeah. Thank you. So those were the differences in the configurations. What that does for you is it produces, and Stu showed this in an animation, which I think is very good, but this is what we get out of this information, which is a cube or a volume showing 3D volumes. Here is this is a bench cut diagram where we show an amplitude time slice here, another amplitude time slice here. This strong reflectors coming across here, the multiples. We'll show you how we got rid of those multiples and processing to actually look at the stratigraphy in better detail. In this one, it's hard to read, and I'll go into it a little bit later. You can see that the shoreline fault is showing in here. There's a shoreline fault. You can see the channels. You can see them both in the plan view and in the cross-section view. So.
I think that what you think you pointed to is the top of rock.
Okay, I'm sorry. I was corrected. This is top of rock and not the multiple.
And what's the geographic orientation on this? North?
North is up.
Yeah, upper left.
Yeah,
And
north.
And the distance scales? How much are we looking at here?
This cube fill is
4 by 6 kilometers. The whole cube that's, yeah. This is a figure in the report, and so all of the scales and North Arrow can be used for reference.
This is just sort of floating out there.
Yeah.
Where
You
is
know,
this?
the thing is that
What are we looking at?
that's
here?
perfect because we talked about that, and we had some other ones we didn't have scales on. We put them in there.
So
if you're talking as a true geophysicist and geologist, you need to have scales.
But this is the box in San Luis Obispo Bay, where and it's the whole box.
This is a portion of the box.
This is not, yeah, this is,
So, okay.
this is you just cut a section of the
Cut a
box.
piece of the box.
Cut a
Okay.
piece.
So it's
But again, this is just kind of an example,
This is an
and I
example.
hope Gary's going to get into some more
Oh,
detailed
we know, but
visuals
it's
as
just
we, with more of the scale on that
right,
as
so,
well.
Yeah.
okay.
Okay, so there's several things that we used for our interpretation. One was using amplitude time slice, and I believe this is the multiple here.
Yeah.
This is the multiple on the time slice here. So we use the amplitude time slice as an example of an amplitude time. Again, sorry, I apologize, no scale on this, Bruce, but this is just for an example. This is at 0.08 milliseconds two-way travel time. We use the smooth similarity slice at the same two-way travel time. And here you can see the faults start popping out at you. And one of the things I like to point out here is that you can look at the cross sections and the profiles, and it's very difficult to see the faults. When you start putting together final note up like this and putting them in the similarity thing, they start popping out at you. And for instance, here is the Oceano fault coming right across here. Here is the shoreline fault coming down through here. But we also went a step further and looked at that with the dip of maximum similarity slice. It's the same time slice. And again, we just enhanced that. You can see the Oceano fault coming across here, and you can see the shoreline fault coming up through here. One of the nice things about this, and one of the things that was a pleasant surprise to me, is that this faulted wedge of material in here appears to be Franciscan and made up of all these various pods, hard volcanic pods, what have you. So we think this is Franciscan, and abutting the Franciscan in this area here is stratified bedrock of Cretaceous sand. Anyway,
So Bruce, this is about 2 miles across, based on the figure in the report, which is figure 2.5. So just read the scale off
Well,
of that.
and again, I don't know if it's significant
Just
to
for a
the-
sense of it, they're just showing how they can see these things
Right.
in general, but it's just for a sense of it.
as a sense. I mean, I'm not ready to accept those conclusions, and I, at some point, would like to know what similarity is, how that was derived from the basic reflection volume, but I don't want to derail the conversation at this point. But-
right, that's a good point, and we can dive into that. We're prepared to talk to you about how that was processed and the tools we use. My intent is to just sort of bring you up to speed in what we're thinking and what our conclusions are, and then you can drill down.
Again, right, when we get to a conclusion, then let's backtrack
Yeah.
as to how that's supported.
Yeah. That's fine. Okay, so I'm just going to spend a little bit of time here now reviewing the Point Bichon area. This is again the Point Bichon area in relationship to the structural blocks of the region. Point Bichon is primarily in what has been called the San Luis Obispo San Luis Pismo structural block, which is in here. Again, this is the older map fault. This is not the final fault map that we've come up with. And this is the seismicity, Hartevac's latest seismicity for the region. And I put this on here mainly to point out to you that the area of interest in Point Bichon is up in here. This is where the seismicity lineament exists. And so the intent of the last survey was to try to image in as much detail as possible this area up in here. So that's what I'm going to just show you now.
Too well in speller.
So again, these are older faults and structures and geology in the area. You have this T-shaped outline, which is where the 3D data was collected, and that's where the 3D volume comes from. And then the purple line actually outlines where additional data was collected, and that was primarily 2D seismic reflection profile. So we use both of these, the 2D and the 3D data, to produce our structural map in the area. This again to show you the simplicity basically of what the Osprey fault zone looked like in this area. And it's hard, I realize it's hard to, I guess the reason you can't see my pointer is because it's about the same color as the wall. So anyway, you see little dots here. These are areas where the seismic reflection profiles at the time this map was produced crossed that fault, and those were the areas that the faults were picked in the seismic reflection profile. This is just basically a track line map for the 2D surveys in there. They're about 100 meters apart. Previous data that was collected in this region from the USGS had a spacing of 800 meters apart. So you can see that we've densified the area considerably with seismic reflection profiles. In addition to that, every 12.5 meters there are 3D profiles collected. So if we showed all the 3D profile lines on here, it would just be a black box. You could see it. And the purples and the blue lines are in the 3D survey area. So again, we obtain an amplitude slice from this. Interesting thing is that you see nice folded reflections in this region. And by looking at where these reflections are truncated or distorted and deformed, you see a fault. This is an older slide showing what we called initially the North 40 West fault. It's now called the Point Bashan fault. And this is the shoreline fault. This is a time slice at 120 milliseconds. And this is the fault map that we derived from the interpretation of the 3D data. The shading in this, we've explained that before, is areas where interpretation was difficult. The rest of the area was really very clear interpretations, but the areas that have shading to them is areas where interpretation was a bit difficult. And in areas where the bedrock cropped out on the seafloor, and that also makes interpretation difficult for the seismic reflection profiles. In multi-beam, you have very good data to work with. Now the interesting thing here is that there's on the Osprey fault zone, there is, as you saw before, we showed it as a single strand coming down, maybe one or two other associated faults with it. Here we have many other smaller, shorter faults that are associated with the Osprey, so it truly is the Osprey fault zone there. So we were able to refine that fault zone, and then we showed the Point Bashan fault zone is coming out this direction here into a region of some small grobens. This is an area of what we think is transtensional. Areas of grobens in here, and then this form of this segment of the Point Bashan fault, it carries on out of the survey grid and trends towards the Osprey, the eastern strand of the Osprey fault to the north. This just shows it in a little bit more detail. The northern part, which we focused on primarily because this was the trend of the seismicity lineament in this area, and we wanted to see if there was faults associated with that seismicity lineament. So on the Point Bashan fault, the conclusions there on the Point Bashan fault was that the Osprey fault essentially shifts from a transpressional structure in the south to a transtensional structure in the north based on the grobens. So, structures overlying the shoreline seismicity lineament are discontinuous splays off of the Point Bashan fault zone. Those are those green faults that you saw on the previous slide. West branch of the Point Bashan fault zone appears to intersect the Osprey fault zone. And the Point Bashan fault is, probably the shoreline fault zone, okay? So,
if I could comment a couple comments on those We did kind of get hung up in nomenclature of this fault between the North 40 West and the Point Bouchon fault. And then even in your second bullet there, where the shoreline seismicity lineament defined by the epicenters located by Hardebeck, with a stated error of something on the order of 1 kilometer, which are on the order of half a kilometer to the west of the Point Bouchon fault. And if these Point Bouchon fault at the surface were to intersect directly with those, if they were the same feature, the west branch of the Point Bouchon is on top of those, within the error of those epicenters. And so the seismic lineament is, for all intents and purposes, in the same place as the mapped Point Bouchon fault at the surface. And I think your conclusion there, trying to distance the surface Point Bouchon fault from the seismic lineament, is okay in the sense that they're not identical, but they're 10 kilometers apart vertically and half a kilometer apart horizontally. And in order to define a fault, you want to just find something from the ground surface into the seismogenic zone. And if you're going to draw a plane, you might as well connect the two dots you've got. The line of the surface and the epicenter at the depth are essentially on the same plane. I don't see a reason to try to disassociate the seismic lineament from the surface fault.
Right. So the reason, the way that we're reporting this information is we're reporting from the data that we have collected. Okay. So first of all, the data that we're looking at is only 400, 500 meters deep. Right. They're very shallow. The seismicity is
6 to 10 kilometers.
10 kilometers down. There's a considerable distance between there and that. Yes, I agree with you. If we could say that plane and we can connect it to what happens. And somebody comes up and says, "Will you show me that fault that goes there?" And we can't do that.
No, there's no data. There's not going to be data from the bottom of your survey down to the seismicity. One of the things I think is missing from your report is what would the dip need to be to connect those? Near vertical.
So that is in the Hosbury chapter of the report. There is a slide. We can
In the sector. Okay.
We can come back and visit that. There is a slide that shows that just exactly what you said.
And so the other kind of really significant conclusions of this chapter are that the west branch ends into a graben which looks to be filled with Holocene sediments.
Right.
Suggesting, best evidence for activity you have on anywhere near this part of the shoreline fault system. And that graben is adjacent to a very similar looking graben on the Hosbury, which suggests a transfer of slip from the Hosbury to the shoreline. And so those, they're all it's all in your report. But I think that connection and those structural similarities between the Hosbury and the shoreline adjacent to each other really do show the connection between these faults and the near surface. So I think that's it's not in this slide, so I want to make sure that that's stated and noted. This chapter 2 in this study does show the best documentation of the connection of the shoreline fault with the Hosbury fault.
Could I ask you,
and activity on the shoreline fault.
Do you differentiate the Hosbury, the Point Bouchon fault from the shoreline at this point? Number one. And number two, is it significant that these grabens, do you agree that these grabens are formed by a transition to transtensional rather than transpressional? Because in terms of the seismic hazard, if the transpression is still there, that's a different deal.
Transpression, I think is what's documented on the majority of the fault zone. And I think it's just at the intersection where you're having a little bit of transtension.
But you believe that those grabens were filled in a trans-extensional?
Yeah, graben by definition are an extensional feature.
Right, but is that due to the step over some fault zone as opposed to some other fault?
Due to transferring a slip off the Hosbury onto the shoreline. In my overall look. so that's, and the second part of your question was what is this fault? And I think that, I just said this, I think this is the documentation that shows that this seismicity lineament is essentially coincident with a through-going surface fault from the Hosgrid into the shoreline where it was previously defined in the shoreline fault report. And so I think this Point-Bouchon fault, North 40 Rust fault, equals, to all intents and purposes, the shoreline fault is what this final conclusion is here. I think that's well documented. So this is that connection, which was on the tornado diagram initially as one of the targets of this whole investigation, I think is well documented in this narrow slice near surface. And when you combine that narrow slice near surface with a through-going connection and Hardeffect's conclusions at seismogenic depths with essentially with what she argues for through-going seismicity lineaments from the shoreline into the Hosgrid. If it's true at 10 kilometers and it's true at the surface, we have a gap in between where we don't have data. But I think the simple assumption is it's a through-going fault all the way down. So that's
So I don't disagree with your simple assumption. I mean,
it's slightly different from the way you presented it, but I think we're saying all the same thing.
Not an assumption, it's a fact.
okay. So what I'd like to do now is to move on to what we call the LESS study, which is basically the PK study. You know, this is all that's what we call it. Anyway, so the objective here was to use piercing points to identify piercing points and to use these piercing points to determine offsets along both the Hosgrid and the shoreline fault. Piercing points such as paleochannel, talwigs, and margins were used, identified and used. Paleo shorelines or strand lines were identified and used. This was in San Luis Obispo Bay. Amplitudes and attributes were used to map structure, geomorphology, and the piercing points. Slip rates were estimated using gauges. The two tools that we had to estimate ages were sea level curves and sequence stratigraphy. And I will discuss that in a little more detail when we get into the various aspects of the
and just because there's a list on a slide, a lot of what these studies depend on is in a 2013 PG&E study that I think was officially part of the long-term seismic program, the stratigraphic framework that was done as a background study for these. And just so other folks know, that was provided by PG&E to the IPRP is not part of this main package, but we've gone through that in some detail. It provides the age control for a lot of the unconformities in the stratigraphy that's being discussed here. So we've had that gone through and had some further discussions about that.
And if you want to ask questions, Hans was the lead on that and would develop that sequence stratigraphy. So he's here if you have questions to ask. Okay, getting back to your point, Chris, is that we identified channels. We looked at areas prior to designing the surveys where we saw in seismic reflection profiles the existence of channels. And we then selected the areas and tried to cover as much of these channels as we could with time allotted to us for imaging them in great detail. Here's an excellent slide. I think this is a slide of a submarine channel. This is what Chris was talking about. You can see a series of channels. They're nested into each other. So there's been some reoccupation, re-erosion, reoccupation channels. Others not so much so. But these are channels that sit very close to the distal edge of the continental shelf out on the slope, and may or may not have a subaerial source. So in this case, we looked at the geomorphology. If we could identify the stack or the sequences of channels that were nested inside each other on one side of the fault in relation to the other side of the fault. Then we felt we had a fairly good geomorphic relationship that we could then say, okay, can we correlate across the fault using this morphology? And so that was one of the things that we did. And what I'm going to talk about here shortly is how we did that in the Estero Bay and the Point Sal area. The other thing, as I mentioned to you earlier, is we use the sea level curve. This is just an example. I'll come back to this particular one when we talk about the shorelines in San Luis Obispo Bay. But just to point out is that certainly subaerial channels erode at the time that the continental shelf is exposed. That is, that after the sea level has retreated and the sea level has dropped, then you have streams and creeks and rivers and what have you that can transport material out across the shelf and erosion takes place. So these occur at the times that the sea level is low. So these spikes, these small spikes that I'm pointing out now, on MIS stage 2, 6B, 8B, 10, and 12, and then you can go further back as well, are times of sea level warming. And so these give us a time marker, if you like, when we think that the channels can form. Okay, so that is one way that we can try to get ages for the channels. This is a complex diagram. I apologize for it.
But just to amplify that point, I think everybody understands that when sea level is low, the streams go across the shelf and can erode into the shelf. So yeah, that's the point. But I think the argument is also made that when you transport sediment all the way across the shelf at low stands, and then you build up the sediment directly at shelf edge, you're more likely to get submarine channels forming at the shelf edge. Is that also correct?
That is true.
So,
but not everywhere, every channel, however.
It's not as good a one-to-one correlation.
Right.
But the concept is low stands are when you form subaerial channels on the shelf, and also when you're more likely to form submarine channels at the shelf edge. Correct. So the timing of channels is tied to low stands, whether they're subaerial channels or submarine channels.
Correct. Correct. Good clarification. So one of the things we struggled with in this investigation interpretation is where on the sea level curve, when sea level is dropping, do channels start to erode? So you need to pick some place on the sea level curve where channels will start to erode. And the same thing occurs when sea level rises. When does erosion stop and filling of the channel take place? So this diagram attempts to do this. This has several different stages, starting with the youngest MS2 over here. I think I'm out of batteries here, you guys.
Gary, need another?
I do. Can I get one?
There you go.
Pass that on.
I was going to consider doing that.
I didn't realize you were
No,
doing it
not
so
there,
well.
not there.
Oh, this is much better, much better. Anyways, these are the three stages, but let's just for an example, I just want to take this stage here. So you have at MS10, you have sea level fluctuating and dropping. Okay, somewhere along this curve, and I admit this is sort of arbitrary where we picked it. We said, okay, right here, this seems to be at a depth of 120 meters, and how we're looking at it is 120 meters. So, and it depends upon where the channel is on the continental shelf, or how close to the distal edge of the continental break that the channel is in. It's starting to erode. So this orange band is a time of erosion. So we say, okay, we know that this channel then eroded somewhere in here. Okay. And then it eroded all the way through the low stand, and the low stand started to come back up again. And somewhere along this part of the curve, the sea inundated the channel and filling began. And so as sea level continued to rise, you fill the channel and you start to deposit sediments over it. And in some cases, you can have a channel, you can have a dip, or you can have another sea level which truncates that. And then as sea level rises again, you have sedimentation taking place. So that's sort of the general idea that we used in trying to pick a time. We looked at both the depth of the channel, the tau depth of the channel, and the low point of the low point of the sea level. Okay, so that was one way of trying to get an age on this thing. And again, I show this slide because here you have channels in the bedrock, and here they're filling. So just looking at where the channels are filling, you're going to say the shoreline, or at least the edge of the transgression, the forward edge of the transgression, is sitting in here. So looking at the channel itself, part of the channel we're looking at, and the sea level curve, we assign an age to that channel into the fill. Okay. The other thing we use, and I'll come back to this slide. It's a bit busy, but I'll come back and use it. Is sequence stratigraphy. So the report that Chris mentioned that they have looked at, it is not part of the report that you guys have received, is from work that Hans and his crew has done on looking at areas where erosions took place, unconformities occur, where you could identify horizons associated with transgression. And those are shown in, you can't see this, unfortunately, these little nicks here. I think that's H20, or H, is that H10 up in the blue? Is H10, that's H10. Blue, yeah. H20, I'll get into the details of that here shortly, but the reasons I'm showing this is that there's a series of horizons that have been identified and these, and aged and dated to a certain extent. And they have been carried around from basically Estero Bay around the corner into Point South, and to a certain extent up into San Luis Obispo, so that we have a time horizon that we can work with. So we, using the sea level curve and these time horizons, then we try to estimate a date. And then we use those ages, the offsets that we found, to calculate slip rate.
You had adequate continuity of these horizons all the way around Point Bouchon into the San Luis Bay?
Yes, the short answer is yes. Not all the horizons, but some of the horizons we could carry around. And they disappeared. Some of these disappeared as you transgressed into San Luis Obispo Bay. The other things that we had to work with was the Willingham report, who had well-hole data that showed horizons, and we were able to correlate some of those horizons. The well-hole data.
Do you want to say a word about the process?
I was going to talk about these horizons. So, as Gary mentioned, these are the surfaces of erosion that are left during by sea level fluctuations. When sea level dropped to low stands, it essentially exposed most of the shelf to weathering and erosion. And then when sea level rose again, the wave action was able to mobilize and remove much of that older material. So these are significant erosive unconformities that are recognized not only on the outer shelf, west of the Irish Hills, west of Estero Bay, and on tie lines, in fact, north and south from Estero Bay to San Luis Obispo Bay, but also into the bays themselves and lapping onto the bedrock of the shelf.
I guess you don't have continuous data there, and within each data set, you had zones that were very difficult to interpret.
Yeah, now I understand the uncertainty. So these horizons were mapped primarily from the USGS data, mini Sparker data set, the 2D survey that was done in 2008 and 2009. So it's on an array of 2D lines that were spaced about every 800 meters that are essentially continuous from Point St. Simeon to Point South.
And Bruce, I think we mentioned this when we were going to go do it for the rest of the IPRP. Tim and Gordon and I went over to the LCI offices to go through some of this data in the software that they have on their workstations and actually both look at some of the 3D data, but also go through the 2D data to see to the extent that we agree with their correlations and agree that they can do these correlations. And these are a lot easier west of the Hosby Fault, where it's relatively deep and continuous and undeformed. But you can carry correlations across the fault in places, there are less continuous lines as you get down to Point South, and it makes it a little harder. But for the most part, west of the fault is relatively clear correlations. And they actually have a map in the report saying there's moderate confidence in their interpretations as you get up into San Francisco Bay. There is very confident correlations and less confident correlations as you go, and then as you get down to this Point South, you lose the continuity of these 2D lines, and so that you have to make these 800-meter jumps in your interpretation.
Why don't you come over here? Okay, so I'm going to go talk about Estero Bay now. So, Hans can chip in. He's right here. He led this work. This is examples of the channels that we found in Estero Bay. They are nested channels. These are also slope channels. They're not subaerially eroded channels. They're submarine channels. And there's a series of channels here. These profiles are shown in here. So they're basically east of the Hosby Fault Zone. And this trace with Hosby Fault Zone. And they're deep.
You might want to mention that the box indicates the extent of 3D data, and then the black lines are the 2D reconnaissance lines that were collected.
So these surveys were collected. This was one survey. The intent was to fill in all of this with 3D data, but due to the timing, was basically we had to leave the area before the high energy seismic survey study started, and this was before disapproval of the high energy seismic survey study. If we had known a little bit earlier, we could have stayed and probably filled out this grid. So we were handicapped in that respect. But what we do is we collect the seismic data on these lines, we call them reconnaissance lines, but then we fill in between those lines with the 3D data sets. So that's why this grid is a bit open, if you like.
And in case anybody with this, I was puzzled by a number of figures like this, and so in case anybody else is wondering, the line, where it says line PBS T1A, if it has a letter designation like that, it's one of the USGS lines from this grid, and so it's done with slightly different technology than what was done for this study, and so the kind of character of the reflections is a little different. So one of the things that made it difficult for me, anyway, to compare channels from one side of the fault to the other. You're comparing different types of surveys.
Yeah, that's because there was two different seismic sources. There was a Sparker source that the USGS used, which is a little bit higher resolution than the Boomer source. And the Boomer source gives you a coarser, if you like, coarser reflections than what the Sparker data gives you. So there is a difference in character, if you like, of the seismic certificate. Anyway, this is the channels that were identified east, on the east side of the survey area. And I'm returning back to this diagram I showed you earlier, and here are the channels identified, and you can't see them well down there in the uninterpreted data. You just have to take our word for them.
Or you could just get closer, they're very well.
Yeah, you can all come up there. Anyway, there, as you can see, there's a series of channels that have been identified in there. And just a little bit about the channel nomenclature that we use, because you see these in your figures, is that we name channels A, B, C, D, E, F, G, so starting from the north and moving to the south. So this is a northerly channel A, intermediate channel B, and a southern channel C. D stands for deep. These are very deep channels compared to any channels that you would find in here. And the W refers to west. So they're the west of the Osprey fault zone. If they have an E on the end of it, they're east. And then you'll see one with little C's in there. That means if the fault zone has been sheared into and you have a central block, these are the central ones in the central one. So this is how we designate these channels. So using seismic stratigraphy then is that you can see that these channels are fairly deep, and there's been a series of transgressions that have occurred since those channels were eroded and filled and covered. This is another method by which we use to constrain the ages of these things. A better way to show this, which is probably one of the valuable aspects of this survey, is that we were able to, and Hans can speak to this in greater detail than me certainly, but this is a diagram that shows us the various horizons, H10, H30, H40, and the relationship to the sea level low stands, for instance, stage 2, stage 6, stage 8, etc. on down. These green lines are where where erosion has taken place. So we know that there's been a transgression across there, there's erosion. The modern shelf break is here, and you can probably say, well, the shelf break is here, here, here. So we can see the migration, if you like, of the shelf break in here. But using these packages and the horizons, we can then say, for instance, this channel then is older than the T05 unconformity. And so this is how we constrain the ages of these things by looking at that unconformity and saying, okay, well, T10 or T20 or T30 above it, so it has to be older than that. In Estero Bay, there was a series of channels mapped. This shows, I won't dwell on this, but there is a series of channels. These are basically the offshore submarine channels. There's other channels here that could have a head that are subaerial, or no, they don't.
Those are all.
They're all deeper than the. Yeah.
They're all channels inside below the shelf.
Below the shelf. Okay.
That's part of the point. Is
Okay.
that even east of the fault, the depth of these channels now indicate that they were initially graded and extended down the slope.
Okay.
So those channels on the east side, can I borrow this?
Yeah, absolutely.
These channels on the east side of the fault are in a block that's uplifting right now, because you can see the evidence for the uplift by the erosion of the seafloor here, and the vertical separation across the Osprey Fault. So even though this block is being uplifted now, the current depth is below the maximum depth of sea level low stands, and these things slope down to the west, meaning that these are just the upstream ends of a channel system that once flowed down the channel. So if you go back and look at these shelf margin sequences, these are all deposited at low stands. So if we want to find the downstream extent of those channels, you have to look below them. So that's why on that bigger slide, you only see channels in the deeper section. The left. Yeah. So that's why we show this broader view, where you see the deeper section that's not part of this shelf margin sequence. This has channels, but the shelf margin sequence doesn't have channels. That's all part of the low stand certificate. So, and then this is the map view showing spatially where those channels were identified on the seismic profiles. Okay. Restoring offset on the fault, let me back up a little bit. So restoring offset on the fault on the Hosbury, you can restore a uniform amount of offset, 850 meters on that western strand, to align this deeper channel with the shallower channel that we showed you a couple slides earlier. That same amount of offset restores this channel down opposite this erosional notch that also has evidence for channels in it. It also restores this deeper channel to about here, which is a credible downstream extension of this dip in the bedrock surface that could have served to channelize submarine flows. So a single restoration of a single amount of slip on this fault aligns all of these deeper channels with credible upstream extensions of them.
Okay. Just for on the record, we have gone through this with ponds, and I cannot convince myself that these channels correlate. It's partly different surveys. But there's a number of features on the upstream, on the upthrown block there, which do not, the three things you pointed out. One is this structural basin, a subsiding syncline that you can see as a growth structure. That's the northern one you pointed out. It's something that could channel sediment, and it could channel sediment, but it's a currently growing structural trough. The one on the south end, which you know is an erosional notch, is the graben on the Hosbury Fault. It's bounded by faults.
Can you point, are these things that are on the?
Yeah, that lower one with the kind
You're
of
talking about
orange,
orange.
that's the growing Wolfson graben actually on the north end of the Point Bouchon Fault. And so I don't see any reason to correlate that with the channel feature at all.
It has channels in it.
It has current growth structure. And the character of the uplifted channel, which in what's labeled and on EE1 and DE, is below the latest unconformity, but otherwise unconstrained as far as age. Yeah, it needs to correlate with something as a downstream equivalent. But that downstream equivalent doesn't currently need to exist, and the current downstream equivalents of AE and BE aren't easily found either, and so I don't find the downstream correlation with DE to be convincing. So that's something that I think we've been through a couple of times, but I think I have some disagreements with some of the technical team here that I'm just not convinced by this correlation.
Well,
So
we'll convince you
you
that.
could continue to work on that.
Do go on.
Can we go back to that slide? I'm probably the least educated on this stuff in the room here, but what are these two unnamed deep channels in the middle that are really short? What's going on there?
These are real channels that were shown on the larger USGS line. That's these.
Mm-hmm.
They may be the downstream equivalents of the two channels that Chris mentioned, here and here. We don't see them at all within the data in between there. So we haven't mapped them and haven't correlated them.
Why do you think you don't see them within the data?
Limitations in resolution, probably.
And it is partly, and Gary mentioned some of this earlier, so just to reiterate, there was a plan for a much bigger 3D volume here, and the 3D volume that got acquired was just along the fault and mostly to the east of the fault. And so 3D volume showing some of these channels west of the fault doesn't exist. And so there's potential for follow-on studies to kind of finish off what was originally laid out here. I think if you really think these channels exist and want to convince me of that.
We can see where that's going.
Well, I think there's a difficulty in my mind making any of these correlations because you just don't get this registered to anything. I mean, again, this is out floating where, you know, yes, it's a sterile bay, but you know, it would be helpful to see where the 3D, where the data comes from that produce those. You know, those
Oh,
may
you
be
mean like track line?
well, just oriented in space here. You know, it's just there's no reference points here.
It's just kind of zoomed in.
Right.
Yeah, well, it's
Well,
zoomed
this
in, but
is-
it's completely disconnected. It makes it real hard to get the spatial registration right. And you're saying that those unnamed deep channels come off of 2D lines that are out there. They're deep, but they're not big. They're not big channels.
Right.
So when we get to
they're
the
minor
question,
features that happen to be at depth.
Yeah.
when we get to the question and answer section, I can pull up the maps that have all of the track lines on it. and show
Again,
exactly.
just as this is presented, where's that 3D volume?
Actually, if you go back one slide, there's a little index map up in the upper right, which does show the 3D volume in the little orange box. And the 2D lines around that.
Long and slender.
Yeah, so it's the longest slender box.
It
just
was supposed to
around
be
the ball.
fatter, but it just, yeah.
So I think there's, the overall study, the correlation of the channels is partly a problem of the capture of data didn't extend as wide as it could have. And so that doesn't help Hans in his efforts to convince them.
Well, but I think
It's
it's a legitimate point of comment for the IPRP that to make these correlations requires a different data set than what we have.
Yeah, I think
Expanded data set. An expanded data set,
Well,
yeah. A continuity. I mean, if these are features that fit all the way across the shelf at whatever age,
Yeah.
we've got to see them cut across.
Yeah.
But Chris,
these are all these are all on the slope. So these are
On the slope,
these are slope
yeah.
channels. Yeah, they're making the point that from the data they've got, they can make these correlations.
Well,
Yeah.
yeah, I mean, there's a push to make a correlation. You know, you have these there. Can you correlate? I mean, so this was an attempt to try to correlate these.
Or can you at least?
And then you also pointed out that these were the upstream, these were the upstream remnants of a system that once did extend downstream. The question is whether we see it or not.
Yeah. It wasn't preserved in the end, did you find it?
I guess another way to put it is, what we have difficulty replicating is unique correlations. Like we see the features that you correlate on one side to the other, but they don't necessarily look exactly the same or same enough to be confident that they're the same geometry, and you can't do it with the chronology. Like if you could do it with the chronology. Now, I do have a follow-up question for Hans. In that figure that shows like all the deeper channels, so is it, I'm not sure if I fully understand it, but it seems like what you're saying is that the younger channels, or younger channels that might exist in that stratigraphy would be further offshore. Because the shelf is building out, and that's why they only cut further out, is that true?
Yeah, because these are channels incised into the slope,
Yeah.
and they extended downslope to the west.
Right.
If you want to look for them on the other side of the fault, you need to look down the slope to the west,
Yeah.
not within the stratigraphy that is the shelf.
Right.
So because there's an outer shelf to the west,
Right.
that outer shelf has grown over and buried
Right.
whatever downstream extent of these channels
Right.
once existed.
And I guess what I'm asking is like, when you look at this figure that has all the channels, this one, there's an absence of young channels.
Yeah.
That's
But
right.
if you go further west on, you start seeing younger channels because the shelf was built out further.
We don't have data for
We don't
that.
have data, okay. But that would be sort of the model, right?
There might be.
As you build
channels
out the
farther
shelf,
Yeah.
you cut the channels higher up in the stratigraphy further to the west.
Yeah.
Right.
But could not that transgression fill or destroy a channel? I mean, it's not guaranteed that channel is going to
To a certain depth.
Right.
It couldn't destroy a channel below the low stand sea level depth.
And that's why we use that low stand in the curve to try to find out where it is, what age was. Okay, so go on, move on. So Hans was discussing this.
Yeah, so this is a characterization of offset. If you buy these correlations, which, there's now some uncertainty regarding whether or not these really are the same channels, but, if this is the same channel, this is how much it's offset. 850 meters plus or minus 800, or plus 800, so the maximum offset could be considering a northward jog in this channel as it approaches the fault, and a southward jog in this channel as it approaches the fault. That's the maximum offset, would be 1,650. A minimum offset would be considering jogs towards each other so the minimum offset of about 450 meters, then the preferred offset of 850. Plus, also, there's vertical separation down to the west across the fault, if you project both of these channel margins toward the fault, of about 100 meters. Then this channel, the eastern trace of the fault offsets this channel by 260 meters plus or minus 60 right laterally, and 40 meters plus or minus 8 down to the west. Incorporating the age model we described based on the stratigraphic horizons, that gives a net slip rate of 1.6 plus or minus 0.8.
And you're just to go back to that, this is below your TO5 uniformity, which is interpreted to be about 500,000 years old, so your age model is at low stands that are older than that.
These would have been developed sometime older than that.
Older than that.
Whether it's low stands or high stands, once you get that old, there's little to be gained by trying to be more precise than that.
Right, and so you're back in the 500,000 to 1,000,000-year-old age range for these channels.
And again, it's because these are buried by a whole outer shelf.
And so your interpretation is that the whole outer shelf sequence that's all built up in this more recent period of more extreme ice ages.
That's right.
Okay, so we have move on? So what I like to do now is just move on down, still staying with the Hosbury Fault and trying to determine slip rates. This is a place that Phil Hogan has worked on, so he can explain it. I'll set this up, and if you have questions, I'm sure Phil will be happy to answer. But this is the area that we're going to look at. One of the things I want to point out is that there's a tremendous amount of data, legacy data from PG&E, USGS data, other data that has been reprocessed for this general area to look at. So these lines have all been looked at and incorporated into the interpretation.
A lot of these grid of lines is in USGS Open Water Report. It's online. Even if you don't have seismic processing software, you can give yourself severe eye strain by looking at the data.
Yeah, all of the USGS lines are online. You can pull them off. Okay, again, here we show the difference between faulting that occurred, that was mapped prior to our survey, or the previous mapping here that was shown from Wellingham et al. In 2013 and Lettuce et al. In 2004. And then this represents the structure that evolved from the work that we did under the last program. And that here is the outline of the 3D volume. There was also 2D lines taken in here, and then I showed you earlier in the slide before this that there's a series of other slides. And generally what happens here is that the Hosgri Fault in this region here, within the 3D survey, it actually trends from a single fault trend here into many trends here, but a distinct eastern trend and western trend, and then converges again to the north and takes off as a single fault. So the Lion's Head Fault, which is shown here, appears to come in a butt against the Hosgri Fault zone, and the Casmalia Fault up to the north comes in and appears to merge in with this Hosgri Fault up in this area. So as far as faults are concerned, we've refined the faults in this region. These aren't necessarily new faults, they are refined faults. We've just been able to drill down and in higher resolution map the Hosgri Fault in this region.
Before you go on, Gary, I had
Yeah.
a question about those slide two
Yeah.
locations. On the right panel, looking at where the shoreline fault may come ashore.
Yeah.
And the same thing with Casmalia. Do you have any land
Yeah.
seismic line
Yeah.
there?
Yeah, but there's, and I'll let Phil talk about this, but just to make it brief here is that there's an oil field in here. And it was the wells drilled that show fault in here that trends along this.
But sometimes when oil wells are drilled, the first couple hundred feet are just blown off as nothing.
Right, yeah, but I mean, they have horizons there that show that it's offset along the trend. So the trend, I mean, we can show you, we will, yeah, we can show you that, those offset horizons. Yeah. And we'll get into that when we, I will talk about the shoreline fault, hopefully soon. Okay. Moving on. Again, in Point Sal area, we have a very, very nice nested channels. In fact, this is the example that I used earlier on. And here you can see where the sequence stratigraphy horizons have been correlated with these channels. And in fact, this is the H10, I believe, horizon coming right across here, which indicates that these channels were older than H10. Now these are again nested. They're submarine channels, and they're on the upper slope. They may have a subaerial component to them, but we don't see that per se. But they are very, very, very nicely imaged, and we use primarily the morphology to correlate these. And I mean, here these are correlatable. I think feel that they're correlatable to each other across the fault zone.
These are all these are 2D lines.
These are 2D.
This is from the 3D bond.
This is from the 3D bond. These are 3D lines, 3D cross sections or profiles. But we'll show the
Can you show the time so you
yeah,
can show the line?
Yeah, we'll show them. And starting off, this is the amplitude time slice. Just again showing the example of this. And I'll show you a couple more here with and without the interpretations. But you can see the reflections. You can see we've identified this area as a channel, this area as a channel, folding in this area here, and a series of faults in there that were well defined, I think. Well defined. I think any one of you here would use those as a criteria for a fault. There was a series of channels, like we showed you in Acero Bay, that were mapped in this area. This is showing all the channels. However, out of all of these channels, there were 3 of them that were looked at to try to see if we could determine slip rates along them. The more northerly ones is a channel that crosses the western splay of the Hosgri Fault zone in here. This channel here crosses the eastern side, but not the western side of the Hosgri Fault zone. And this channel, F, crosses the entire fault zone. And so I'm going to dwell on this one because this is the one that I think is the best correlatable channel in the region, and that we feel that we have high confidence in some type of offset along there. Again, I'm just going to point out, I've said this before, but here is the age model, or the age, how we determine age. Age 10 is here, so these are all younger or older than age 10, and older than the, oh, age 30 is it, yeah. Phil just pointed out to me, it's hard for me to read here, but age 30 is right in there, I think, Phil.
Off to the right, and it just,
Right,
it's
green.
pinches out over about where the age 10 is.
Pitches out before it gets to the FE3 channel.
That's
So right in here.
Yep.
Yeah. It's hard for me to read this, probably you too, but the bluish one is age 10, the green one is age 30.
And just for reference, age 10 being 20,000 years,
Right.
being so much younger than any of the sediments we're talking about,
Yeah.
it just means everything above that has been removed. It's not part of the story anymore.
Right.
Age 30 being about 120,000 years is getting into the age range of what we expect the sediments to be. So that's an important marker. If you can clearly tie that into the channel someplace.
Right.
And then the other ones are interpreted to be older than that. This is also a place, and maybe Phil, you wanted to talk about your confidence in these, because as we went southward in the USGS data, the USGS data has this crosshatch of lines and high lines. It gets down in the southern limit of Visceral Bay, but then as you get towards Point South, they only have parallel. You only have the lines perpendicular short and then gaps between them, and so it gets a little tougher to correlate.
That's correct, Chris. And the line spacing on the USGS lines is 800 meters when you get down towards Point Southward. It's 400 meters farther north in most cases, and some cases even denser than that. So sparser coverage on the USGS regional lines in this area. Nevertheless, we were able to trace H30 with a moderate level of confidence all the way down to the Point South area. H40 we were not able to trace with a high level of confidence. H10 is visible throughout the area except for where it's up in the bulbal pulse. So H10 we have a very high degree of confidence in. That's the MIS2 during the last glacial low stand, being 20,000 years ago.
And your confidence of interpretation is, even though there's gaps in the intermediate gaps between each of these successive lines, you're okay with that?
Yes, and we will be showing an isopath map of the H30 horizon. You can see that it's not continuous throughout the 3D survey area. But those slides are coming up, so I think we'll get into that. This F channel, which is found in the southern portion of the survey area. We've got a high degree of confidence in the offsets, as Gary will explain going forward. This particular line in the inset you can see is line 1368 towards the eastern part of the survey area, and lies in close proximity to one of the USGS lines where we identified a paleo channel prior to the surveys, which is one of the reasons why we targeted this area for slip rate constraints on the Osprey Fault in the first place.
Okay, so let's focus on channel F. Here it is an amplitude time slice across channel F, and uninterpreted section here, interpreted section here, and you can see that the faults are very well displayed in this region here. And here you can see the margins of the channel. This is channel FE3. And basically what that means is channel F on the east side of the fault, and is the third or the shallower of a nested channel complex.
You can also see the margins of the deeper channel, which underlies that just to the north of the FE channel margin.
Right. All right. And then here is what it looks like in the central part. This this is an FCE1, and then what it appears to be here, the margins well displayed. Well, it's actually here and here, and then the fault goes across here. So we have a high level of confidence that we are able to correlate this structure, this feature, this morphology across the fault. And so taking that, the towel-wed of FE3, carrying it down here, there's several solutions that you can come up with. You can assume that the towel-wed continues right straight across, maybe all the way across to here.
It's gonna be a long voicemail.
I didn't quite get that.
No.
Therein lies the record.
Yeah.
Anyway, it could have taken a sharp left turn here or a sharp right turn here, and so this gives us minimum and maximum offsets that we figured into the displacement along this fault. Now, our preferred is, of course, that the towel carries right across and is offset to carry right across through here. Again, here is the maximum and minimum. And so, looking at FE3 here and FW3 across here, all the way across the sand to the concrete also, we get 600 to 650 plus or minus 50 meters of offset.
So while a range of values were considered here, the data paint a very clear picture, and then further enhanced our understanding of the offsets across the entire Hosbury Fault Zone in the southern point cell survey area.
We've been at this about an hour and a half. It's probably time for a sketch break if we could find some point in the slides to do that shortly.
So let's finish up through the slip rate at Point Sal, and then we'll take a few minutes during a break.
Okay. I'll try to make this fast.
Okay.
I actually been trying to make it fast. Okay, so then we also considered the sea level curve, and this is the paleochannel age model for Point Sur. And so for the channel F age, we prefer stage 10 down here at W3. And I won't go into this table in detail, but we can if you want, because here we give both what we think is the minimum and maximum offset, and then our preferred offset. And then we also give you we come up with three different ages that we think, stages that we think that this canyon could have been eroded. But our preferred, as I mentioned earlier, our preferred age is MIS 10. And using MIS 10 with a preferred offset of 600 to 650 meters, we get 1.75 to 1.90 millimeters. But our range in values, extend from here to here, but this is our preferred.
So just to explore the upper end of that, fill that age range at what does he have? At 138 assumes that the channel and the unconformity age 30 are essentially the same age, so the channel and that unconformity are kind of merge into each other. So is that what kind of weight do you think we would put on that? How likely is that scenario where you have a 140,000-year-old channel?
I give that a very low weight.
That's a very unlikely scenario.
Yeah.
And do you see any place where that uniformity and the channel are intersecting, or
Yes.
one cutting the other?
I think closer to the eastern splay of the Hosbury, the age 30 horizon comes up and goes across and thus fossilizes the top of the Elio channel deposits, the FE3 channel deposits.
Okay, so if that age 30 goes completely across your channel, then you're saying that's a nearly impossible scenario. And So the next one down is you would, curious why you jump all the way from 6 to 8, or 6 to 10, and 10 is your preferred. Do you have a significant weight on channel correlating with MIS 8?
We consider the MIS 6B, 138,000 year age, to be a minimum age for the channel. And we also considered MIS, or stage 8B, which is about 240,000 years or so. And that's possible. But west of the Osprey, we see a fairly thick stratigraphic sequence between H30 and the top of the paleo channel. And so it's likely that H40, possibly other nonconformities, are within that interval. So we could a much higher weight.
Younger ages are possible, and you haven't been able to correlate H40 or any other nonconformities into that area. But the thickness of the sediments, do you think they're likely to be there? And this is likely to be older, channel likely to be older than H40 or some of the others.
That's correct. We looked at the Willingham et al. Sediment accumulation rates, which were well constrained by offshore well data and high-energy seismic surveys throughout the Santa Maria Basin. ELP nonconformity, that's the really late Pliocene nonconformity, which is dated between 2.7 and 3.5 million years, is a basin-wide nonconformity found in every well throughout the entire offshore Santa Maria Basin. We mapped that surface up into our survey area, and so that forms a very clear stratigraphic horizon. There's another good nonconformity that's younger than that we term the near-top neogene nonconformity that also comes up and merges with the early late Pliocene nonconformity. But in terms of the sediment accumulation rates, if you look at the Willingham et al. Map, which was published in 2013, the long-term sediment accumulation rates for this area are about 20 to 30 centimeters per 1,000 years. And based upon that, one would expect that the H40 horizon would be on the order of 60 to 100 meters below the seafloor, which matches very well with what we see west of the western splay of the Osprey in the Point Sal area.
I'm trying to make sense of this. Does the presence of a larger number of channels, especially newer channels, does that mean higher seismic activity, or am I totally off?
No, the easy way to think of this is the slip rate, these resulting numbers, is the energy budget. It's how much energy is available to be released in earthquakes. And so the higher slip rate equals higher hazard. And so that's the key thing we're trying to get at is the slip rate on this fault is how much hazard is at the plant. It's the one number that most closely correlates with hazard is the slip rate on the Osprey fault. Any high slip rate is high hazard.
And does the slip rate depend on the number of channels?
Not the number of channels, but the amount of displacement in the channel.
Okay.
So we're trying to say how old is the channel and how much has been offset by the fault. Because that slip rate, that average over time slip rate, is energy to be released in earthquakes.
But indirectly, it could. If you had a fault, let's say you had a stream coming down and intercepting a fault, and that slip rate was high, and it moved, you have a channel on the other side of the fault. You move that, another channel forms, and moves that. So the more channels you have forming, you can get more channels down that way. So indirectly, yes, then you could see that.
That could happen too.
That could happen.
But
right.
the key number we're after here is the slip rate number.
Right.
That's what the whole discussion is aiming at. Okay.
Is this a good time for a break?
I think
It's a good time for a break.
Well,
Oh, yeah, we're okay with it. We said she could. Yeah.
Rochelle Beck wants to make a little announcement.
Well, I have been filming you, so I'm going to ask your permission, but the PUC did say it was okay to film. Unfortunately, I'm a horrible filmer, so you have a lot of feet, but I do have your voices, just so you know.
So where's the second? So you filmed this or you've not filmed this?
I have filmed you.
Yeah.
Our feet.
Yeah.
Mostly your feet.
It's a public meeting, so I told her it was okay to film it, but realized that people should probably be aware of it. Yeah. Yeah.
Thank you.
Gary.
Okay. Okay, so we're going to jump into San Luis Obispo Bay. This slide basically shows the 3D survey area in this region here. And other lines, primarily USGS lines here, but other lines, Necton lines. Earthquake that occurred right here at this red dot. And what was the date on that film?
August 10th, 2000.
August 10th, 2000. And then there's a series of other epicenters that exist in this area here. The interesting aspect of it is, at least at my feeling, is this represents sort of the southern end of the seismicity zone. We have very little seismicity mapped down further south here. And this is sort of the southern end of the seismicity lineament that is up to the north and northwest.
And it's also the largest event in the shoreline fault zone catalog.
Finally, it occurs right near the juncture of the Los Barros Fault, Oceana Fault, and the shoreline fault. Note how straight and linear the shoreline fault is, whereas the Oceano Fault and the Los Barros Fault have a more curvilinear fault trace.
Sousa Rock exists right here.
Can I just go, just a kind of cartography question. On that image, you show the Pecho Fault in a heavy dashed line and then a light dashed line of queries, but the shoreline fault in dots, which usually means concealed. You're showing the bedrock surface. What's the line types mean?
You're right. Dotted Oceano and shoreline faults infer concealed faults, whereas the dash faults and queried are inferred. We weren't able to connect the western display of the Pecho Fault in the northern part of the block with another fault trace farther south, which is why we query it.
That's queried.
Yep.
But the dotted, meaning they're concealed by the sediments that aren't on this image.
Right. That's right.
But
That's right.
But the Pecho cuts through those faults? Cuts through those fault sediments?
It's a lower degree of confidence in the North Pecho Fault, that's why it's dashed queried, but it's also buried.
So dots queries maybe.
That might be.
Everything buried. Nothing comes to the surface through the sediments.
That's correct. All of the Los Barros Fault comes very close to the surface. There's outcrops immediately north of the Los Barros Fault and the hanging wall. That fault. The Los Barros and the Oceano Fault are both reverse faults, whereas the shoreline fault, as far as we can tell, has a nearly pure vertical or horizontal 10-to-1, 15-to-1 sort of strike slip to vertical ratio.
Just something I've noted on a lot of images is these. Some of the best defined faults are shown in dotted lines. I don't quite understand. It's a presentation more than a science.
I think it's an attempt to show that these things, you would not see them on the seafloor. Yeah. And it's just like a concealed fault going across the sea. I mean, that was the intent. But it should not take away from the fact that this is a well-defined fault.
As Gary mentioned, it's extremely visible in the top bedrock surface, smooth tip of maximum similarity volume. There's no doubt that the shoreline fault and the Oceano faults are there. They're very well defined and they're very, very narrow.
Yeah, and you showed that in the previous slide. Yeah. And then it shows up in the dotted line on the submarine axis.
Okay. And so if I could ask at this point, the similarity measurement, is that a fairly simple correlation coefficient between adjacent traces? It's like taking the derivative of the wave field?
That's correct. And we've got a separate PowerPoint presentation on attributes if you would like to see that later on.
We can get through the rest of the 75 slides.
Yeah. No, I just, it's an edge enhancer, basically. And with the signal, you enhance the noise as well. So at a, in certain instances, I think the image does speak for itself. In other instances, if you're enhancing noise, you're making noise sharper,
you have to ask, what are you looking at? That's just an aspect of the reflection cycle.
Okay, this slide basically shows the differences in mapping. Here is the mapping before we completed the 3D survey and then looked at the USGS line and other lines to the south here. Basically what it shows is that we have the shoreline fault coming here. It's well defined, as Chris mentioned, in this area here. And then we infer the fault coming down here. And mainly it's inferred because we go from very, very small spacing between track lines in this area to wide spacing. This is 800 meters or so apart to looking for where the fault is. But there is evidence that there is some faulting taking place in here, and we show that as a continuation of the shoreline fault. In the southern part, these are newly processed lines, or older lines, but the newly processed lines, the Necton lines. These are, I'm sorry, I don't have the uninterpreted part on here. We can certainly supply those. But this is illustration of the faults that we carry on down and call it the South Patrial fault on this side here, these on the left, and the shoreline fault on the south. And this is where it comes to the shore. I don't have a slide to show the oil field there or the onshore, but we have that if you want to look at it. Okay, so let's go to piercing points on the shoreline fault.
Actually, just to wrap up one item on that glass, because I think we've been seeing little bits of this study for San Luis Bay since 2011 or so, and not great to get the full report. But one of the things that we commented on in our September 7, 2011 report was that the plans for studies of slip rate and shoreline fault seem to be going in the right direction. And a secondary focus of those should be the connection of the shoreline fault with other faults onshore. And we didn't really expect much to come of that recommendation. And that last slide really shows that you've got that one.
And you probably saw the other backup figures, supporting figures in the report, or in the appendix of the report, that show the onshore data in the Guadalupe oil field, where there are literally hundreds of wells that have been used to constrain the location of a northwest striking fault that goes offshore more or less at the mouth of the Santa Maria River and is in direct alignment with the offshore traces of the South Patrial fault and the shoreline fault. Gary, if I could go back just one slide, please. I wanted to point out one other thing. Can I have the pointer just for a second? Okay. I wanted to point out that the before study fault map here shows the Patrial fault. This is the South Patrial fault, as mapped previously by others, PG&E and Willingham et al., and the North Patrial fault. Note that the South Patrial fault over here more or less has the same alignment as where we have mapped the shoreline fault here and the South Patrial fault. We think this Patrial fault and the shoreline fault are integrally related. They're probably splays to one another and linked together as depth. And we were able to extend it based upon the new data that we dropped into, we digitized, scanned, digitized, dropped into SegWi, and put in a Kingdom Suite down here in southern San Luis Obispo Bay, and then we're able to tie it together with the onshore oil well data in the Guadalupe oil field. Oh, and then also the North Patrial fault here is a similar strike and alignment with the Oceano fault in this general area, but we were able to refine that based upon additional data through here, and thus be able to link up the Santa Maria River fault and the Oceano fault with the mapped trace of the Oceano fault so clearly imaged in the 3D volume.
And just one additional thing, you show the shoreline and South Patrial as two parallel lines through that whole thing, which is what you do when you have to connect the dots that are 800 meters apart. And the chances of them being separate and parallel for that entire distance seems to be small to me.
We've got about 15 legacy archive high energy lines where both splays are clearly imaged.
Okay.
And so they can image the image that...
You don't think they're azimuthalizing and
There may be some discontinuous segments of these two faults parallel to one another, but in general, on line after line, on the high energy surveys, we can see two separate but pretty proximal faults that go very steeply.
I was just curious, because that seems to me like the kind of fault pattern you show when your data isn't very dense. And what you've shown, when data is really dense, you have a much more complicated pattern.
Yeah, and more confidence too.
Yeah.
With your map. Yeah.
Before we leave this slide, and it may be a topic more of conversation for the next meeting, I'm looking at the Wilmar Avenue fault, and there used to be a San Luis Bay fault, I think, Wilmar Avenue to the southeast of that. There was complexity in the older information that suggested there might be a connection between those two, and the new data shows definitive sense that they're not. What was the basis of that change? Because there doesn't seem to be high density data in there close to do that. Is there a particular reason that that change was made?
Well, yes. Within the 3D survey area, we could clearly image the Los Barros fault, and then to the east, we went back and looked at the legacy archive data, and again scanned and dropped some of those lines into SegWi and into Kingdom Suite, and were able to correlate the continuation, the eastward continuation of Los Barros fault between the 3D survey area offshore and its nap trace onshore. It may be possible, it's quite likely that the Wilmar Avenue fault also hooks up with it, or slip is transferred between the Wilmar Avenue fault and Los Barros.
Gary, can you point out the San Luis Bay fault? Yeah. So it's just not labeled on the figure, but it's still there.
Yeah.
Okay.
But it's queried now, where it used to have the thrust bars.
Well, and again, so you're saying that where the Wilmar Avenue fault is changed in its depiction, there's actual, at least legacy data that goes over that spot?
Yes, although it's much clearer on the Los Barros fault than it is for the Wilmar Avenue fault. The high energy offshore legacy archive lines weren't able to get into the shallow water where the Wilmar Avenue fault is mapped.
Okay.
You can only see it on the USGS line.
Okay, thank you.
Okay, so let's move on to talking about piercing points and trying to determine offsets along the shoreline fault. Here's an uninterpreted amplitude slice showing the shoreline or the strand line, paleo shoreline, strand line. Here it is outlined in orange, and the shoreline fault here. That location is right about down in here. This is a contour map of that showing the same thing. There is two different shorelines that exist right in this area where the shoreline fault crosses these paleo shorelines or strand lines. One is at 84 meters depth, and the other is 92 meters depth. And both of these are offset equally. So we'll talk a little bit about the offset. This is what it looks like close up. Here is the shoreline. Here's the shoreline, paleo shoreline here, the strand line. Here's the shoreline fault coming down through here.
The shoreline offset by the shoreline fault.
Shoreline, okay, I knew I was going to get that off. Then you would have to visit that, Chris.
But and we did go through this in the 3D volume at LCI's offices and looked at this three-dimensional surface that's offset. So you can see this surface that's sloping down to the northwest, and then it's offset along the fault in that 3D volume. It's not too bad in the 2D images, but it's really convincing in the 3D volume.
So the offset, there's 9.4 meters, plus or minus 6 meters offset from here to here along the fault. So we have a fairly competent offset. And now to determine the age. And what we've done is projected this very irregular feature into the plane of the seismic reflection profile here. This is it here. And here is the H, what is that? H10 horizon here on the blue, and the H30 horizon on the green, coming in and merging with the H. So it appears that the shoreline lies beneath the H10 and the H30 horizon, and above the H40 horizons, which is showing coming in here, and above the bedrock surface. So this is what we use for constraining the age of that shoreline. In the seismic reflection profile, again, here you can see the H10 horizon coming through here. This is Holocene or Pleistocene sediments in here. Again, we projected that shoreline into the plane of the seismic reflection profile, and we use this for getting ages. You've got something to say?
H30.
H30, yeah, here's H30 right in here.
Yeah, and line location is shown on the inside of the upper right. So clearly the paleostrand lines predate H30 and H10, and the top bedrock surface, as we saw on the previous slide, H40 pinched out or onlapped onto the bedrock surface at a lower elevation, below 120 meters, farther to the west. So we've been able to bracket the ages of these two paleostrand lines across the shoreline fault to between H30 and H40.
And this is the shoreline fault right there. Okay, so when we look at where the 84 and 92 meter shoreline lies right in this area here, as far as when it could have been eroded during the sea level low stand. And below this here is H30, here is H40, and thus we have a preferred age of around 150 to 180,000 years sitting there. So we looked at four different ages that are shown on the left side here, but our preferred one, and I won't go into the details of all the other ones unless you would like me to, or like one of us to do so. But what we get using that offset along the shoreline fault and the age of 160,000 years, we get 0.06 millimeters per year for the shoreline fault at that location.
And just so it's clear, the uncertainty is not whether the strandline feature is between the conformity shown on the figure is H30 and H40, but it's whether those really are H30 and H40, because you have to correlate that all the way out across the bay and into deeper water where those unconformities are defined.
Yeah, there's an age uncertainty in terms of the age of H30 and H40, and whether those in fact do correspond with stage 6B and stage HB, as the seismic stratigraphy report.
Okay. So another piercing point that we looked at, which is Channel A. This is showing the location of Channel A, which is Sousa Rock, and here's the trend of the shoreline fault right in here, shoreline fault zone. Channel A Cowwick comes down like this, it appears to be offset and comes on down like this. This is a slope back showing the margins of the channel in this area here. The red means it's very steep, and so the margins are pretty well defined here with this red band on both sides, the shoreline fault coming through like this. The interesting thing about this is that the shoreline fault can be seen coming through here, and you can see it in the sediments. So it is offsetting, the shoreline fault here is offsetting the sediments. In the seismic reflection profiles, we see the H10 horizon right here, coming across here, and it cuts off or truncates the fill within the major fill. There is another nested channel that's showing it. I don't know if you can see that very well, but right in here is a nested channel. And here we can see the fault that projects up, not all the way through the fill, but up through about halfway through the fill in this area here. If we look at a perspective view of the channel, we can, and we take the towel-wig, we can bring the towel-wig here, and it appears to be offset right laterally, which we would expect along the shoreline fault zone here. This is the Oceano fault zone coming in and merging with the shoreline fault at this location. And so what we get out of that is about, on the towel-wig, we get 30 plus or minus 10 meters of offset. If we look at that nested channel I pointed out to you, there does not appear to be any offset on that nested channel. Now that doesn't mean there isn't any offset. This is within the resolution of our data. So within, let's say, 6 meters, we don't see offset. And again, you can see the fault coming through the sediment in this area here. And we have offsets. These are differing offsets on the margin. In this area here, we have 20 plus or minus 10 meters. And here we have a difference of 40 plus or minus 10 meters. So the margins are offset, but they're offset differently. And this could be that there's some erosional offset taking place there, as well as structural and tectonic offset. So if we look at using the age of the channel A of 430,000 years, that's our preferred MIS 12, we get 0.07 millimeters per year. That's in contrast to 0.06 millimeters per year that we got using the shoreline. We also considered these other ages as well, MS6B, and all the way back to MIS 35. That's quite a range, but we tried to capture what all the possibility would be, and again, we end up with a preferred 0.07 millimeters per year on that.
And so one of the key observations then is to compare the rate that we got for the shoreline with the rate that we get for the Haas-3. It's easily a factor of 10 less. So in terms of overall priority in the ranking scheme, the Haas-3 is still considered the controllable source, the faster moving of the two faults.
This is also much lower than an estimated slip rate estimate for the shoreline fault as presented in the 2011 shoreline fault report, which was 0.2 to 0.3 millimeters per year.
So now we're, all the numbers you prefer are below 0.1. This is not sure the right place for this question, but it seems like all of the uncertainty in these slip rates, and to some extent in the Husky fall slip rates you presented, are in the dating of either the channels or of the uniformities. And so this is the sequence stratigraphic model that we built with the ages of H30 and H40 and the cutting of channels in the low stand is a complete model, but then you have to say, well, the model could be wrong, and we have these other alternative ages for each of these features. Are there other ways to get solid dates on the channels or the unconformities or the sediments that would allow you to toss out a few of these alternative models from your sequence integrity? Is there a better dating method you can use?
Well, I mean, there's better methods to date sediments than what we had available at the time, sea level curves.
Would any finer details in the dating require sampling, or is there other things that you can do geophysically?
I can't think of anything geophysically that we can do now to define those dates any better. I mean,
So
we've tried to figure out other ways in which we can date those horizons. I mean, well, one of the ways was going back and looking at the wellhole data, but the problem with wellhole data is that the the upper parts of those wells are thrown away, you know, you don't
nobody
get
wants
those.
dirt.
So you're okay at the older dates, but the dates that you want are the younger ones.
But in some areas, higher resolution seismic would help you get image the top 20 meters where you have the bubble pulse, and sometimes the H10 is lost in the bubble pulse.
Right.
So if you had some chirp data, then at least you have the top.
So you're in the same, you get better high resolution in the shallow chirp data.
Right.
And that will tell you, that's helpful.
Right.
In telling you the stratigraphy. But unless you get a date, unless you know what is, you know, a particular reflection, you're back to saying, okay, I think that this stuff is all Holocene, or that, you know. So that's,
It only buys you so much. Right?
It only buys you so much.
And for most of these models, your best defined conformity is going to be H10, which doesn't matter in any of these models.
Right.
It's all H30, H40.
Yeah, that's correct. We have a very, very high degree of confidence in the age of H10. And it's well documented worldwide. You can see it very clearly.
Really
on chirp data, you can see it very clearly on the plumber data and the sparker data.
And it's just too bad it doesn't really make a difference here, because this is all older material, older channels.
So my question here is, given the tools that we're using to constrain the ages here, what is the specifications that we have? How high a resolution in age do you think we need to get?
I was just asking you how high resolution can you get? I don't know what the requirements are. The requirements overall, you know, the AB 1632 report was to decrease the uncertainty in seismic hazard evaluations.
Right.
That was one of Stu's lead off slides. The tornado has gotten narrower. So to that extent, you know, this is a step forward. So all steps forward are better than any steps backward. But you know, how far can you go? I think that's kind of where I was trying to ask.
Well, to follow up on that comment, Chris, and perhaps to put this in a different perspective, you know, we're talking about age dating in sort of an absolute chronological framework. However, all this data is to be used in probabilistic hazard assessment,
right,
which can account for uncertainty in ages, in rates, not only the weights that we give in the logic tree, but just in the whole methodology. So there's a point where, yes, you have uncertainty, but you can address it adequately to move forward and then to demonstrate the answer.
In these numbers that you're showing for the shoreline, you go from very low to very low. And so it's not that big a deal. It's a bigger deal on the shoreline where it's on the hospital. Where that is your highest slip rate in the region, is your highest hazard. And so if you had a factor of 3 uncertainty like you have here on that fault, then you'd have it.
You could capture it, but what do you do with it once you have it here?
So what I think we need, though, is that, okay, so how, can we improve upon these dates? Are there methodologies in which we can improve on this date? Yes. How much improvement do we need to do? What is the range of slip that is going to make a significant difference in hazards analysis? And once we get that number, then we can say, we can then select a tool, for instance, that we would need to go get that information.
Yeah, my sense is that, I was going to ask you this question next. My sense is once you're in the range of, all of our preferred models are below 0.1, and the next nearest fault is 2 millimeters a year, this fault no longer really matters. Is that?
That's correct. That's correct. And really, when you're asking what is the accuracy you need to get in the slip rate, we are at the point where our ground motion model uncertainty is dominating the problem, so you're making an improvement, but the net effect is not a huge change, not a huge improvement in the reduction of the uncertainty, because that's now the big player.
And if you had a, this is from, I'm just looking at the high slip rate value versus the preferred thing, it's a factor of 3 here. If you were at a factor of 3 still on the Hosby,
that would matter.
Yeah, that makes a difference. Here, it's a very low number versus a very low number. It's no longer significant in a probabilistic.
Yeah, so our low to our high is more than factor of 3.
I'm looking
It's
preferred.
5 or 5
I'm looking
or
preferred,
10 or,
the preferred
yeah.
to high end. Either way, it's all low numbers.
I'd also like to reinforce what Gary said earlier about this master channel, that it appears to be unfaulted within the resolution of the data, which is 3 meters horizontally, 2 meters vertically. This suggests that the shoreline fault has not ruptured since sea level rose and transgressed across this area 10 to 15,000 years ago. We don't see anywhere else where the shoreline fault appears to have ruptured up into the Holocene sediments. And we can see that contact, that boundary very clearly on the data. This reinforces the fact that it's a very low slip rate fault.
And
We actually jumped ahead a little bit.
yeah, the other part of that is this is having offset of that channel infill is evidence for late Pleistocene offset on that fault. And then all the way at the other end of the north end of the Point Bouchon fault, having the filled graben is evidence for latest Pleistocene movement on that same fault system. So I think you're bracketed by maybe not proven Holocene, but latest Pleistocene displacement on this fault. So I think that's a significant step out of these studies, is that on both ends of the shoreline fault, as was originally thought. You have latest Pleistocene displacement, low rates, but it's active.
As indicated with the microseismicity.
As indicated by the microseismicity. Plus, you've extended it down what used to be called the Pedro fault, and so it's a longer active fault.
And I guess that's one of my questions is, okay, we've done some measurements, best we can tell it's not moving very much. Is that consistent with the microseismicity energy budget? Not something that I can, that I can weigh in on. And it would be helpful at some point to synthesize all the different slip rate measurements at different points along the shoreline. Because now 3 or 4 of them have gone by. And I guess my last question is, in terms of the grabens that are at the north end of it, do we have any way of estimating their extensional rate? I mean, the extent to which they're filled, is that?
I puzzled over how to make a slip rate volume open
out of that.
Thing out of that. I couldn't do it.
Well, there is a method in which that can be done. The problem is achievable.
I mean, among the questions is we have come to think of the shoreline fault as one feature now, from where it intersects the Hosbury to where it lands on shore back toward this point south. I mean, and in terms of our evaluation of this, I think that's one thing that seems to be emerging. I don't hear any
I think that's
controversy.
That's what I'm hearing from and seeing out of these reports, and that's the conclusion.
And so along that entire length, what do we know about the slip? Are we seeing any slip? Can we talk about a creeping versus a locked fault along the length of that?
I kind of assume all faults are locked until proven otherwise. And these 2 slip rates, which they've just presented, both the channel and the shoreline, are the best documented slip rates on that system. I think they're usually, if you look at slip rate studies on faults, these are relatively well constrained in the world of slip rates.
You have to, in the 2011 report, the slip rate on the shoreline fault was essentially between 0 and 1, and simply based on geomorphology and what do we see worldwide with faults that have this kind of exposure. There was no offsets or anything that was used at that time, because the moment rate that you get out of or slip rate you would infer from the microseismicity is a very difficult thing to get at, but we tried it and it was a low number, so it was near the low end of that range. But I think rightly so, Gene Hardebeck criticized us, saying that's not a reliable way to get slip rates, but that was all you had at the time. Now you've got something, so this is a lot better than what we had before.
I
think the LESS study has really enhanced our understanding of the shoreline fault and achieved the goals of AB 1632, both in terms of constraining the geometry and location of the shoreline fault, as well as constraining the slip rates.
So,
And you have a bonus fault for us.
Okay, so anyway, to wrap this up, we're pretty close to wrapping this up, believe it or not. One of the other channels that we looked at was along the oceanic fault. The oceanic fault is reversible, so what we're seeing is vertical displacement here. And this is showing the oceanic fault. Sorry. Showing the smooth similarity slides here. This is it showing on the slope map, and again showing on the contour map on the bedrock surface. These are the seismic reflection profiles. You can see that this channel appears to be eroded into the bedrock and eroded into this pleistocene wedge of material that comes up here. I believe this is H10 sitting right along here. So it's below H10. And so our preferred, for all those channels, most all those channels are going to be around H10. So using those ages, MIF2, and we don't see any offset on that, but let's say that it's within the resolution of the TNS. So we'll give it 2 meters of offset.
We actually didn't see vertical separation.
Vertical separation, I'm sorry, but not
2 meters.
Yeah, not strike slip. And so what we come up using this age in the preferred offset is 0.1 millimeters per year. So that also is pretty close to 0.7, 0.6, 0.06 millimeters per year on the shore.
Yeah, this is a reverse fault versus a strike slip fault. It appears to be pretty much purely vertical. We don't see any evidence for strike slip motion on the oceanic fault.
And were there previous studies of the Oceano as it goes on land in the LTSP? Is there a previous date for that? I'm trying to remember it because earlier work on that suggested doesn't.
Yes, there has been early work, including a seismic profile across the oceanic fault onshore. I don't recall the published slip rate is on the oceanic fault onshore.
But the seismic lines in the appendix.
That's right.
The work that was done for the LTSP incorporated interpretations of this vibro-sized line onshore and boreholes where they tagged older surfaces like the Paso Robles and the top of the sedimentary section beneath the onshore Santa Maria Basin. And the types of slip rates they were getting onshore were in the range of 0.05 millimeters per year.
Same order of magnitude.
Yeah.
Okay, conclusions.
Yeah, and actually that Oceano is a good place to wrap up because that's a little bit of where we're going next meeting, which is talking about the uplift of the Irish Hills and the faults underlying the Irish Hills and all of the
accessible to anybody who's interested in looking at it?
Because that's part of, what we've created here is what we call a legacy database. So this is information that we have posted on the web, we posted with these independent academic institutions to make that available for decades. This is a long-term commitment to have that data available. It is publicly available.
Do you have the image of that?
Get it?
Okay? Conclusions. So,
Maybe.
the resolution of the data, the southern shoreline, the column is in the wrong place here, sorry. Southern shoreline fault zone appears not to have been active since last transgression, or somewhere around 12,000 years. Preferred estimated Hosbury fault zone slip rate, and we're placing this from the work that we did on the point south, because we feel that is the most greatest correlation, best correlation, is 1.75 to 1.90 millimeters per year, and that's based on channel F offset, and that is actually corroborated by the combined slip rates of channels A and B. So I didn't go into detail with it. I think that all fits that supports our preferred slip rate. Preferred estimated shoreline fault zone slip rate is, we give it 0.06 millimeters per year based on paleo shoreline offset, because we feel that that's the best piercing rate to use.
I just want to make sure that we firm up the dates for the subsequent IPRP meetings today.
Right, and that's actually our last agenda item. I wanted to make sure, I'm not very shy about asking questions as presentations go along. But I don't know if anybody else, members of the IPRP, had questions for the various presentations you've heard and want to follow it up. Are we tied to a 4 o'clock?
Yeah, pretty much we have to.
Exit room 4?
Yeah,
so
about 4.
Well, let's firm up the date of the last meeting and then finalize questions then. I think we had talked about a meeting among the IPRP of November 17th. Is that still on everybody else's calendar?
Planning around that. And this date was to go over the slip rate studies and the studies of the connection of the faults in chapters 2 and 3. Don't actually recall what the on-land seismic surveys and the faults beneath the Irish Hills would be the main topic of our next meeting on the 17th.
And we're also going to address some of the comments from Dr. Hamilton.
Yeah, and part of the tectonic model of the Irish Hills is alternative tectonic models of the Irish Hills. And that's one of the proponent models that's come up in the JAC process. We have a whole chapter in our reports about is Doug's model for the Diablo fault and other faults that are allowing for the uplift of the hills. So that's part of this.
Do you think it would be
part of our next meeting.
Would it be beneficial if we started our meetings, let's say at 10, and then went like from 10 to 4 with a lunch break, so that we'll have more time?
Yeah, I think this is.
We don't want to rush through this.
I think we've got through everything in our 3 hours today. You know, I got what I was looking for out of this meeting.
Okay, so you think 3 hours
but,
next time? Or?
Yeah, I think starting at 10, going 2 hours and taking a lunch break. And, you know, if we get done by 2, that would be a bonus.
All right.
Yeah, for those, I mean, I think that's a great thing for those of you who got to get back out of the city. You know, if we get done before rush hour, that's a gift. Yeah,
that's fine.
And that works for me. That's why I'm fine with that.
That's tentatively planning.
Will there be an IPRP report?
So our plan is to do a IPRP report summarizing what we've heard and what we have. Our review comments for these parts of the CCCI report. And it's, we will try to go back to the recommendations we made in the IPRP reports 2 and 3 that are relevant to what we've heard today, and also go back to what we summarized in IPRP report number 5 about the Hosbury slip rate and how these studies update what we know there.
And Chris, would it be your plan that we would have that report nearly final and make it an agenda item on the 17th of November?
That's probably a good idea.
To present our conclusions.
Go over that. We've tried to do our report within 30 days. November 17th is less than 30 days from now. So maybe we could have put that together. But we will have circulated a draft among the IPRP at least, and we will try to briefly summarize that.
And talk about what it would take to finalize that report perhaps.
Okay, that's feasible.
And at a point, that it's appropriate, I'd like to just make a couple comments on the next topic, but we want to finish up today first.
Yeah, I think that's, any other comments on today's topic of slip rates and slip rate studies?
One of the comments I had was with the Hoskery and Shoreline, both there's segments or portions of the mapped fault traces, and the piercing points were in one particular segment. I know they're hard to find anyway, but you have multiple segments parallel in the zone, and all this measurement is based on one segment, one portion. And I understand that that's all you have, but there's other segments that go through that you're not.
Well, I think you're talking specifically about the shoreline fault zone.
Well, the Hoskery in particular too, there's the new information shows a lot of segments within that zone.
You mean fault splays at the
Splays,
surface?
sure, yeah.
But not segments. in
Not
the long
segments,
fault.
splays. Let's call them splays, yeah.
There's two parts to that, and
To answer that right now, it's going to be difficult, but
talk about
I was
the
just
shoreline
wondering
fault.
if
the shoreline fault, all the measurements are made in San Luis Obispo Bay, and this is a reach of the shoreline fault before it intersects, hooks up with the Oceano fault, the Los Barros fault, and the other faults that come in that knot near Sousa Rock.
Right.
So is slip now being transferred from those faults onto the shoreline as it becomes a simpler structure as it then goes towards Point San Luis. So we don't, because we did not have the opportunity to find piercing points, we didn't find piercing points, it's hard to answer that. But the idea is that you probably do get a transfer slip onto a single structure from multiple structures as that converges.
Stu, I think he wants to say you got 3 parallel strands of, the east, west, or whatever, and you measure the slip rate over one, but you need it over all of them. Is that what you're trying to get at?
Perhaps I could
That's what we did on Channel F.
Right.
And Channel, for instance, Estero Bay, or the Point Sal area, that Channel F was down. There was actually a central segment, but there was another channel in central block. So that channel was correlated across 2 different strands of the Hoskery fault, across the western strand and the eastern strand.
I think that one of the, maybe what Casey is frustrated by is, in all of these reports, there's detailed discussion of channel A, and then you didn't find the correlating channel, so that's all kind of dropped. And then channel B is kind of dropped. And channel C, you kind of cross one strand and then up and not the other strand, so that it's not followed up on. It's not until you get to channel F that you actually find the channel on all the way across the zone. And this is true in Estero Bay. As you kind of work, you describe the channels from north to south, and the Point Sal is from north to south. It's only until you get to the channels all the way to the south end where you find something that you actually think you can correlate all the way across. And so if you were putting these reports into a paper for publication, you just throw out everything except the one you file all the way across. And you wouldn't even mention it. But we appreciate all the data.
I know that works, but the other side of that coin is that, well, why didn't you guys consider these other channels?
No, we did.
And so our intent was, we'll just give you all these channels, and they don't. So, I mean,
we have to talk about what's constrained and what's not constrained. And if we don't have the slip rate near the plant, we have a hole in the data as far as I'm concerned.
And so and actually this is something that we will discuss in the report from the IPRP, is how do you weight the various slip rate studies that have been done. We have the on-land studies that were done as part of the LTSC, and that's published, and they were done quite a long time ago. We have the more recent studies that were done probably with PG&E money through SGS by Sam Johnson and recently published. And then we have these 2 studies that were done specifically by this team for this project. And so each of those comes up with a slightly different number, and they're distributed along the fault on both sides of the plant. And so one of the things we did in report number 5 is say, this is the range of slip rates you get from each of these studies. And this is what you get from geodetics and other background information. And so where do we think the best estimate is for the seismic study at the plant?
The other part.
And this is not coordinated with but it's the same thing that the shack process is doing. And I've given some preliminary information into the team for the shack process too. And so, we're going to get to about, we're going to try to do that summary of what's appropriate for use and is a slip rate summary for the Osprey that we think is the best range of estimates.
When you calculate the energy budget that you're going to have for a fault, it's not just the part across the offshore of the plant, it's along the entire length of the fault segments that you're doing. So for the Osprey, really we need the numbers averaged over 100 kilometers. So we wouldn't, we do it simpler than trying to say it's going to vary. We just get what's the total available from that fault, and then we balance it that way. So
one of the things that it's now much easier is there's this tectonic model as you come south on the Osprey fault.
Right.
Slip is bleeding off onto the other strands. And if the amount of slip that's actually bleeding off of the Osprey onto the shoreline is an insignificant number, your calculation for the Osprey got simpler.
Right.
I think a different way of looking at it, the same kind of question would be, at what point is the amount of slip rate relevant to the vulnerability of the plant?
Which has seismic source characterizations, so rates of earthquakes and their locations and geometry, what's the ground motion model, what's the site response, and what's the structural model. So you need to look at all of those and their relative constraints to decide how much you improve in one part of the model versus another.
Yeah. The tornado diagram really helped me understand how things kind of go together.
I would like to offer a specific answer to Katie's question with respect to the Osprey fault at Point Sal. When we went into the study, we were trying to find a piercing point on the Osprey fault at a location where there was a single splay of the Osprey fault. And in the Point Sal area, there was one splay of the Osprey fault as mapped by all previous studies, including as recently as 2012, the Johnson et al. Paper using the USGS lines. We also wanted to find a piercing point where there was a paleo channel above the shelf break, and we identified such a channel in that vicinity. Based upon that, we went out and did the 3D surveys, and lo and behold, there wasn't just a single paleo channel. We found evidence for 6 paleo channels, only 3 of which cross splays of the Osprey. In the northern part of the survey area, there was just a single splay of the Osprey, and in the southern part of the survey area, there was a single splay of the Osprey. But there was a restraining bed, and as Gary showed earlier, 2 major splays of the Osprey in the center part of the survey area. The 3 channels that we focused on were channels A, B, and F. Channel F crossed all 3, or all, both the eastern and the western splay of the Osprey, so that's our best piercing point. However, channel A crossed the western strand and channel B crossed the eastern strand. And the combined slip rates of channels A and B matches that of channel F, so it provides corroborating evidence, although the channels didn't go all the way across. We didn't use channels C, D, E, and G because they were only found on a single block.
Makes sense. So, I think we're basically done. I wanted to mention that I think you talked about 3 meetings that are initially planned. We haven't set a date for the 3rd one yet.
Yeah, we had mentioned, but toward the end of December.
Yeah, so we will try to do that in December. There's probably way too much going on in everyone's calendar in December. We'll try to make that work. And that will focus on site conditions and ground motion model.
Correct.
So I think that's the last thing.
early January is always better than trying to squeeze it in.
I know. I have the strong suspicion that this meeting will slip into January. We will be unable to find a quorum anytime in December. Yet unable to schedule a day at my own time.
Okay.
Any other, Rick, do you have further comments?
For looking ahead to the next meeting, I wanted to just make comment particularly to my IPRP colleagues. I've spent a fair amount of time looking at the interpretations of the fiber size and weight drop lines on the onshore data in Chapter 7. And to be honest, I see a whole bunch of faults interpreted there that I cannot confirm as I look between the uninterpreted section and the interpreted section. These faults go through reflection events in complete contradiction in many cases to the assumptions that were made or the methodology of the interpretation. There are changes noted in amplitude that for the life of me I cannot see. And I note that the interpretation of every fault in Chapter 7 on the 2D lines is noted as dashed lines queried. At the end there's a very confident-looking fence diagram of solid lines. And to be honest, to my eye, I don't think those 2D lines constrain anything regarding the tectonics of the Irish Hills, both beyond, fingers width
downside to give you my working draft.
I would hope that my IPRP colleagues would take a little time and just look at these and see if they can make some definitive case. And as you look in Chapter 7, there are a couple of instances of alternative interpretations that are substantially different from the previous one. And I wonder then what the universe of alternative interpretations are. So I think that's fundamental. It's not whether the interpretation is wrong, but whether the data actually
what I've been doing.
That's the question I'd like to bring forward.
Recognizing this is working.
Stu, you got that?
Well,
that's where we're starting from.
I caught it. So I would like to suggest, based on experience, very favorable experience we had working with you, Chris, before this meeting, you had the opportunity, you and your team, to spend time with the consultants to go through the data in quite a amount of detail and interrogate both us and the data.
Yeah, it's better to look at 3D volumes than PowerPoints always.
Yeah, so I am extending that same invitation to you, Bruce, and to your folks that we are available to spend time prior to the 17th of November and let you interrogate us and the data so we can understand your issues, the exact locations, and it'll help I think smooth out the meeting on the 17th.
And I'll make every effort to do that, but given the relatively short interval to the next meeting, that may be problematic. I would hope to have at least one of my IPRP colleagues with me at that time, someone who has a little more geologic intuition than I do, and see if we can pull in. Where would the consultants be located?
Well, it's either Walnut Creek is one good location. That's where the authors in Chapter 7 are located, or we could do it down in the city.
Okay.
So your choice.
So working maybe with Chris and others that might be interested, again, if I could get colleagues to just look at these sections and get a sense of what I'm not seeing, tell me if I'm wrong, but I will make every good faith effort to do that. But
we will try to schedule a working meeting, probably at the LCI offices in Walnut Creek in the next couple of weeks. When you can make it.
Oh, thank you. We'll see what that looks like, and I'll start tomorrow.
We'll
figuring that out.
We'll start trading emails tomorrow
Sounds
about
good.
scheduling something.
Thank you.
Thank you.
Yeah, I'll coordinate with the LCI folks.
I'll let them know.
Warn them at the office.
Okay, with that, I'd like to thank everyone for coming and participating in our meeting, and